Okay, so let's take a look at another question where we're identifying the intermolecular forces of a molecule. Here we have the molecule CH3OH, and this molecule actually represents methanol. So what that actually looks like, if you wanted to look at the shorthand notation of it, it kind of look like this, right? Or if you wanted a visualization of all of the bonding structure, bonding atoms, and the covalent bonds, right? It would basically kind of look like this, okay? So that's the structure, but we're going to kind of do it piece by piece. Now, if you already understand how to conceive of the structure, you can kind of skip this next portion off. But let's kind of do this step by step, as it is a great way to understand the procedural formulation of these problems. Okay, so got that erased. If we're looking at this molecule, methanol, CH3OH, right, well, we have 4 hydrogens. Oh, tablet's acting up again. Sorry, guys. There's 4 hydrogens. There is 1 carbon. There is 1 oxygen, right? So out of these species, carbon is the most likely central atom, because we said before, although hydrogen is the least electronegative, it is too small to be a central atom. So we usually go with the second least electronegative species, which is carbon. Carbon usually is the central atom. Okay, so the central atom is carbon. And what we're going to do here is we're going to figure out a few parameters, such as the valence electrons as well as the total electrons each species needs to form a stable octet. So we have carbon here, we have 4 hydrogens. And I draw out the valence electrons for each of them. And there is 1 oxygen, right? And I'm going to also write down the electronegativity values that we're going to be using later. So if you wanted to kind of verify that carbon is a central atom, right, it's going to be the second least electronegative species, right? So the electronegativity of carbon we're going to look at as 2.55. Of hydrogen is about 2.20. So these are the values that I have, guys. Obviously, this might differ from what you guys are using. And for oxygen, we'll use 3.44, okay? So looking at this in the columns, we're going to look at the total number of electrons to form a stable octet. This last column to the right here, we have total number of electrons in the valence shell, or the total number of valence electrons. I'm going to denote that or abbreviate that as TeV. And for TES here, we have 8 electrons for carbon. For each hydrogen, we should expect 2 times 4, which is going to give us 8. And for the oxygen, we should also expect 8, right? In total, the TS, or the total number of electrons to form a stable octet for all these species and to essentially create our molecule, we would need a total of 24 electrons, right? Because it's 8 plus 8 plus 8. For the valence electrons, carbon has 4. Each hydrogen has 1, but there's 4 of them. And oxygen here has 6, right? So if we add all these up, then we should have 14. So if we're looking at this, then we can assess how many bonds would we expect to see in our structure, in our molecular structure. So the total number of bonds, Tb, is equal to the total number of electrons in the stable octet minus the total number of valence electrons, and divide this by 2. Okay, so in this case, you get 24 minus 14, divide this by 2, which is 5. So there should be a total of 5 bonds. A single bond counts as 1 bond, a double bond counts as 2, and a triple bond counts as 3. Really, the total number of bonds represents the total number of bonding electron pairs. Okay, so if we have 5, we should see 5 bonding electron pairs here. Okay, what we could do at this point is we could think about a potential arrangement. So we have a central atom here, then we have the hydrogens, which should have 1, it should be monovalent, that means it should have 1 bond, and oxygen should also have a bond from each side. So this is the best potential arrangement, because we know oxygen should be divalent. It should have 2 bonds, right? And we can't form a double bond because we need 5 bonds. And if you think about the 5 bonds, this is probably the best bonding architecture, right? Each of these single bonds counts as 1. So it does take a little bit of trial and error, guys. But you can understand that, carbon has to be tetravalent, that it has to have 4 bonds. Each hydrogen should be monovalent, it should have 1 bond, and the oxygen should be divalent, it should have 2 bonds. So this is the only proposed structure that fits, and it also fits with the 5 total bonds. So that's why this formula it's pretty useful. It's a great way to kind of design your structures, trial and error wise. It'll give you a little bit more information, right? So this is our potential structure. If we think about our Lewis dot structure, right? Carbon, I'm going to draw out here in blue. It'll donate one of its electrons to receive an electron from a hydrogen and also from an oxygen, which I'm going to change colors here. Let's make this baby blue. Okay, and this oxygen will also donate one electron to this other hydrogen here. So what you can actually notice here is there isn't just a single central atom, there's actually two. Okay, so the carbon will act as one of the central atoms, we'll call it C1, and oxygen will act as the second central atom, right? So the carbon central atom, we have 4 bonding atoms. For our oxygen central atom, we have 2 bonding atoms. Okay, so you're not always going to have one central atom, guys. I think you'll see this when you draw it out. You can have more than one, right? So far in the previous examples, we've looked at just a single central atom, but it does get more complicated when you have polycentral atoms, right? So if you have a very large molecule and you have multiple central atoms. Okay, so try to be on the lookout for that. But whenever you see that the total bonds are greater than 4, this is a great indication that you're going to have more than one central atom. Okay, so based on this, what we need to do is we need to actually look at each central atom independently, right? So looking at central atom 1, which is the carbon, right, we need to assess lone pairs, bonding atoms, and the total number of electron groups. So in central atom 1, we have basically, for this carbon here, we basically have 4 bonding atoms, 0 lone pairs, and the electron groups is the sum of the bonding atoms plus lone pairs, which you should see 4. So it should be tetrahedral at this site. Okay. For carbon 2 here, or the central atom 2, did I say carbon 2? Sorry guys, central atom 2. The central atom 2 here, which is this oxygen, remember that there is these electrons here, right? You can see that here. These are the 2 lone pair of electrons. This has 2 lone pairs, 2 bonding atoms, it's the carbon and the hydrogen, and it also has 4 electron groups. So the geometry is still tetrahedral, but this geometry coincides with a particular molecular shape. And the molecular shape here is an angular bent shape. Okay, you can call this bent, or we can call it V-shaped, or the full name of this is angular bent V-shaped. Okay. Putting these two together, if we were going to draw this, carbon central atom 1 would be tetrahedral. So if we're looking at the tetrahedral template, I'm going to make these hydrogens, and this hydrogen and this oxygen in the plane of the page, and the other 2 hydrogens, one's going to go out of the plane of the page, one will go into the plane of the page. Now the oxygen should be angular bent, so it should have its 2 lone pairs that looks like that, right? We usually draw these little blob that looks like alien heads. They basically represent the orbitals, because an orbital holds 2 electrons, right? It shows the orbitals of the lone pairs on the oxygen, right? And this oxygen will then bind with this hydrogen. So this angle, you can be a little familiar with the angles. If you forget VSEPR structures, guys, take a look at the video I'm going to add to the end of this video. It's another video where you can actually go through all of this stuff, VSEPR structures, Lewis dot structures, you know, do a quick overview. Well, not a quick overview, but a long overview of intermolecular forces. So you guys can go through that. You don't have to go through the entire video. It's a pretty long video, so just you know, pick and choose certain regions that you guys need to kind of take a look at. So this angle here is 104.5 degrees, right? Or you can say less than 109.5, same thing. This is what the structure will look like. So it's a combination of 2 structures, right? In general, it's gonna coincide with the tetrahedral geometry, but there's 2 types of molecular shapes in the tetrahedral geometry, right? So once you have this, then what we need to do is we need to assess electronegativity differences. Well, if we're looking at electronegativity differences, we need to look at the different types of covalent bonds that we're going to be looking at. So there's actually three types of covalent bonds. I'm going to highlight them. One of the types is the carbon-hydrogen bond. The other type is, and I'll use different colors to show that. The other type is the oxygen to hydrogen bond, covalent bond. And the third type is the carbon to oxygen covalent bond. So sorry about the different shade of green. Hopefully you guys can distinguish between the three types. And all we have to do is do the calculation for these three types. So you can imagine that the larger the molecule is, the more complicated it is. But we're still using the same principle. So that's why the step-by-step procedure could be really useful. So let's look at the electronegativity difference between carbon and hydrogen. So in this electronegativity difference, you're doing electronegativity of carbon minus electronegativity of hydrogen. I've noted the electronegativity differences here. Sorry, the electronegativity values here. These are the ones we're going to be using. And our scale based on this, I'm just going to write down here. If the electronegativity difference is greater or equal to 0, but less than or equal to 4.5, sorry, 4.5, 0.45, sorry about that, 4.5 is too high. This is a non-polar covalent bond. Okay, so I'm going to abbreviate it as NPCB, right? If the electronegativity difference is greater than 0.45 but less than 1.7, this is a polar covalent bond. And these are the two, because we know this is not ionic, we won't look at the last interval. So we just want to distinguish between, is this a polar covalent bond or is this a non-polar covalent bond? So if we're assessing this, the electronegativity of carbon here, 2.55, minus hydrogen, which is 2.20, which is 0.35. Okay, so this tells us that the difference between carbon and hydrogen is basically a non-polar covalent bond. Okay, I'm going to just abbreviate this with a capital N so we can kind of distinguish between it easier. Okay, then we can assess the electronegativity difference between carbon and oxygen, right, which is the electronegativity of oxygen minus the electronegativity of carbon. The reason I'm using an absolute value, guys, is because I'm just looking at the magnitude of it, right? And in this scenario, we get 3.44 minus 2.55. I think if I did my math properly, this is 0.89. So this is, in fact, a polar covalent bond. So a dipole moment is being created here. So what that tells us is that in our structure, there is a dipole moment that gets created towards the oxygen. So this is a partial negative. This carbon is a partial positive. And lastly, let's take a look at the electronegativity difference of oxygen and hydrogen, which is the electronegativity of oxygen minus the electronegativity of hydrogen, which is 3.44 minus 2.20. If we calculate this, right, we can get 1.24. So this, for sure, is the largest electronegativity value we have. This is definitely a polar covalent bond. So we have another dipole. This one's going to be longer, actually, because it has a larger value, right? But remember, this is just a sketch, guys. This is partial negative, and this is partial positive. Okay, so based on this, what can we get from this? Well, let's determine if this molecule is polar, right? So I'm just going to get some space here so we can kind of show that better. Kind of bear with me, guys. But you can imagine that this is a little different from the previous question because now we had multiple central atoms and we actually have two polar covalent bonds. So we actually had two dipoles being created, right? So I'm just getting rid of some of this so we have some more space. This eraser tool is not the greatest, but just kind of bear with me a little bit. Whoops. Right, so this is a little different from the last two examples that we did. Okay, I think I got most of this erased. Okay, so I think we can work with this, right? So in this case, I guess, if you have OCD, this is probably not the greatest thing. Okay, so what we can do here is we think about what our molecule will look like. We'll call this step 7, right? We have, and you can imagine the importance of VSEPR structures at this point. Okay, so let's put the hydrogen out of the page. This is in the page, right? And this is going into the page, okay? And we said that there is 2 dipole moments. I'll just use the same color this time. There's one dipole moment here, partial negative, partial positive. There's another dipole moment here, partial negative, partial positive. Okay, so we'll call this dipole moment 1. We'll call this dipole moment 2. So mu sub 1, mu sub 2. If you want to find the net dipole moment, guys, you have to do vector addition. So the net dipole moment, because this is a vector sum, you're going to add mu1 plus mu2, right? So if I add that in, if you're doing vector addition, you do tail to tip, tip to tail. So this is a projection of vector mu1. This is a projection of vector mu2. What we're doing here is when we summate the vectors, the resultant vector that you actually get here is basically here, right? So this is the net dipole moment. You can notice here that because we started here and we ended up here, and it didn't add up to 0. This value is not equal to 0, so therefore we get a net dipole moment generated, right? And then this net dipole moment shows that there is a dipole. So this portion is negative and this portion is positive. So this, in fact, is a polar molecule. So one thing you want to understand is that just because you have polar covalent bonds doesn't mean a molecule is polar, right? You need to make sure that all of the dipole moments, when you do the vector sum, that it's not equal to 0. If it's equal to 0, that's a non-polar molecule, right? It doesn't matter if it has polar covalent bonds. The molecule as a whole, all of the dipole moments, if they cancel out, that means that the molecule isn't polar. There isn't a dipole being created, right? So that's something that you want to understand. So because this is a polar molecule, after we did the summation of the dipole moments, then we can understand that, okay, because it's a polar molecule, we can understand some of the intermolecular forces that are found. Okay, and the intermolecular forces that would be found here in this structure, all molecules have London dispersion forces, but you're going to have dipole-dipole forces, right? And this molecule also has the ability to undergo hydrogen bonding with itself. Okay, well, how does it undergo hydrogen bonding? Well, if you think about 2 of these next to each other. Okay, so I'll just kind of redraw this. Right, and this hydrogen bonding would be found in cohesive and adhesive forces, assuming that the solvent itself was water, right? But if you had 2 of these molecules next to each other, just kind of drawing that out here, you guys can see it. Okay, so that's 2 methanol molecules. Right, methanol is an alcohol, right? This is not the same as drinking alcohol, guys, so don't get it twisted on that. Drinking alcohol is ethanol. It has another CH2 group, right? So it has another carbon that's present, and there's 2 other hydrogens. And essentially, if you think about this, this is partial negative, partial positive, partial negative, partial positive. And you can actually see that hydrogen bonding can exist, right? So you can also see there is hydrogen bonding between the oxygen and the hydrogen, but you can also get dipole-dipole forces between the carbon and the oxygen. So this is a dipole-dipole force, but then this here is a really strong dipole-dipole force called a hydrogen bond that has a very significant or very large electronegativity difference. Okay, so that's the summary of the intermolecular forces of this molecule methanol. Hopefully you guys understood this or were able to go through this. Feel free to pause and fast forward or basically rewind parts of the video so that way you can understand the procedure. Try this yourself. It's the best way to learn this stuff. And I'm also going to attach the link to the full video that outlines, Lewis dot structures, VSEPR structures, the different types of intermolecular forces, as well as some sample questions that look at some physical properties. Okay, so that's basically it for this question. Congratulations on finishing the video. To reward your attention and determination to learn and enhance your skills, we've created a new reward system this year. Each time you complete a video, you will be rewarded IQ points. Depending on the length, difficulty, and type of video, instructional versus question-based or both, you can be rewarded different levels of IQ points. These IQ point rewards will be either 10, 20, 50, or 100 points. Our goal for implementing this system is to enhance your motivation and improve your daily productivity. Use the amount of IQ points you earn each day to reinforce and gauge your commitment towards your education. And while you do this, remember to like, comment, subscribe, and share our videos. Your continued support will assist us to release more free educational content in the future. Our collective goal at Course Concepts is to assist you towards academic success, one step at a time, because success starts with a single concept. So we want to thank you for being a member of Course Concepts.